When the brutal Soviet winter hit and wool supplies vanished, Red Army soldiers faced a terrifying reality: freeze solid or find a miracle. That miracle wasn't a new coat, it was a desperate experiment in chemistry. Discover how engineers turned fragile sheets of paper into a high-tech lifeline against sub-zero extinction. Welcome to the Survival Bunker, where we study the brutal reality of surviving war zones, sieges, and battlefield collapse. Today we examine one of the most counterintuitive survival engineering decisions in military history. Not titanium, not advanced synthetic insulation, paper. Chemically treated, industrially layered, pulped wood paper, deployed at mass scale to prevent millions of Soviet soldiers from freezing to death during one of the coldest winters ever recorded on the Eastern Front. This is not a curiosity. This is a case study in what desperation and applied chemistry can produce when the alternative is an army that cannot stand up. The winter of 1941 arrived on the Eastern Front with a violence that defied planning. By November, temperatures across the front had plunged to -40 degrees Celsius, a threshold at which exposed skin freezes in under 2 minutes, and standard military equipment stops functioning. Rifle bolts seized, engine oil solidified, artillery shells had to be warmed before firing. For the Red Army, the cold was not just an environmental condition, it was an active tactical threat multiplier layered on top of an already catastrophic logistical situation. Operation Barbarossa, launched on June 22, 1941, had, shattered Soviet supply infrastructure across a front stretching thousands of kilometers. Rail lines were severed, depots were overrun or destroyed during the rapid German advance. The industrial machinery of the Soviet textile sector, concentrated in western cities that were now either occupied or under siege, had been evacuated east under emergency orders, leaving an enormous gap between production capacity and frontline need. The standard Red Army winter issue was built around wool felt boots called Valenki and quilted cotton-padded jackets called Telegreka. Both required significant material and manufacturing time to produce. By the autumn of 1941, the supply chain for both had, effectively collapsed under the weight of simultaneous military and civilian demand. Millions of soldiers were going into temperatures capable of killing an unprotected man within hours with inadequate or non-existent winter clothing. The physiological consequences were immediate and honestly well documented. Frostbite casualties on the Eastern Front in the winter of 1941-42 numbered in the hundreds of thousands across both sides. The Red Army's medical records from this period show frostbite injuries classified as combat casualties, men who never saw a German soldier but were removed from the front line because their fingers, toes or limbs were no longer functional. Hypothermia operates along a precise physiological track: core temperature drops, cognitive function degrades, extremities lose sensation, and the body begins to shut down circulatory function to the periphery to protect vital organs. A soldier who cannot feel his trigger finger cannot fire his weapon. A soldier whose core temperature drops below 32 degrees Celsius cannot make effective decisions. Below 28 degrees, he will lose consciousness. The Soviet war machine understood this equation. The question was, what to do about it when the materials for conventional solutions no longer existed. The answer came from industrial paper production, specifically from the properties of cellulose, which is the structural polymer that forms the primary component of plant cell walls, and by extension, paper. Cellulose in its raw form is not an insulator. Sheet paper actually conducts heat reasonably well and absorbs moisture rapidly, which in fact accelerates heat loss rather than preventing it. The engineering challenge was transforming a material with those properties into something that could hold body heat against a -40-degree environment. That required two interventions: chemical treatment and structural design. Soviet engineers applied hydrophobic chemical treatments to paper stock, processes designed to reduce the material's moisture absorption rate. The key problem with any insulating layer in a cold, wet, or high-exertion environment is, well, moisture management. Sweat and condensation penetrate insulating material and conduct heat away from the body far faster than dry air. Wool manages this through its natural crimp structure, which wicks moisture away from the skin while maintaining trapped air pockets in the fiber. Treated paper needed to replicate this function artificially. The physics of insulation are honestly pretty straightforward. Trapped, static air is one of the most effective thermal insulators available. Air has extremely low thermal conductivity, approximately 0.024 watts per meter, Kelvin at standard conditions. The problem is that air moves. Convection strips heat the moment air circulates. The function of any insulating materials, wool, down, synthetic fiber, or treated paper, is to trap air in small enough pockets that convection cannot occur. The material itself contributes almost nothing to insulation. The immobilized air trapped within it does the work. Wool achieves this through natural fiber crimp and microscopic air chambers. Treated paper, layered with deliberate gaps between sheets, created a similar architecture. The cellular structure of wood pulp fibers, particularly in thicker craft-grade paper stocks, contains microscopic voids that persist even after processing. When multiple layers were assembled with deliberate spacing, the resulting composite trapped air across a series of thin, parallel chambers. Each chamber was small enough to suppress convection, while the hydrophobic treatment slowed moisture penetration. The thermal conductivity advantage over a simple fabric layer was, well, definitely measurable. A single layer of fabric provides negligible insulation, really. But a multi-layer paper composite with trapped air achieved insulation values that, under dry conditions, could actually approach those of a thin wool layer, produced at just a fraction of the material cost and, importantly, using industrial infrastructure that had not been destroyed or evacuated. The manufacturing pivot from textile mills to paper mills was not, a gradual transition. It was an emergency conversion ordered under wartime priority directives as the scale of the clothing shortfall became clear to Soviet command. Paper mills in the Ural region and Siberia, areas well beyond the German advance, were among the industrial facilities that had remained operational throughout the 1941 crisis. These facilities produced kraft paper and cellulose board stock for packaging and industrial use. Converting a portion of their output to insulation material required really just modifying output specifications rather than rebuilding production lines from scratch. The chemical treatment processes, things like sizing agents and hydrophobic coatings, were compatible with existing mill chemistry. The construction process for the layered paper insulation suit followed a specific assembly logic. Sheets of chemically treated paper were sandwiched between thin outer fabric layers, typically a coarse cotton weave that provided abrasion resistance and helped maintain the structural integrity of the paper composite beneath. The paper layers themselves were not single sheets, but, corrugated or loosely crumpled assemblies that created the air gap architecture required for thermal performance. Flat, tightly pressed paper layers compress their air content and lose most of their insulative value. The assembly process had to maintain separation between layers to preserve the trapped air pockets that made the entire system work. The cost arithmetic drove the decision at scale. Wool for a full winter uniform required months of processing across a supply chain that included animal husbandry, shearing, cleaning, spinning, weaving, and assembly. Paper insulation could be produced from available pulp stock, treated, assembled, and distributed in a compressed industrial timeline. The suits were understood from the outset to be temporary, disposable insulation layers intended to bridge the gap until conventional textile production could be restored and supply lines rebuilt, not permanent replacements for wool and cotton quilting. For a military force managing simultaneous production of weapons, ammunition, vehicles, and food across a wartime command economy, the trade-off was straightforward. An imperfect insulation layer that could be produced now and distributed to millions of soldiers was worth more than a perfect wool uniform that would arrive too late. Archival Soviet military and medical records from the winter of 1941 to 42 document the conditions in which these improvised insulation solutions were deployed. Soldiers on static defensive positions, men holding siege lines around cities like Leningrad, Moscow, and Tula faced sustained exposure to extreme cold with, honestly, minimal ability to generate movement-based body heat. In conventional winter warfare doctrine, soldiers are advised to keep moving to generate metabolic warmth. But a soldier in a fixed defensive trench for a 72-hour rotation simply cannot do that. The paper composite layers, well, they provided measurable benefit in exactly this scenario. Under dry conditions, still air, no precipitation, the trapped air architecture functioned close to design parameters and actually extended the safe exposure window for soldiers who were otherwise inadequately dressed. Accounts collected by Soviet military historians and medical officers describe soldiers layering these composite garments under their standard-issue outer clothing, using the paper insulation as an intermediate thermal barrier between skin and the environment. The limitations, though, were significant and well understood by the men using them. Moisture was the primary failure mode. A soldier who sweated heavily during movement, crossed wet terrain, or was exposed to rain or wet snow would find the hydrophobic treatment insufficient to prevent moisture penetration over sustained periods. Once the paper layers absorbed moisture, their thermal performance collapsed. Wet paper conducts heat rather than trapping it, and, well, the garment became a liability rather than an asset. Durability was, well, really a secondary constraint. You see, paper tears under physical stress. The cotton outer layer offered some structural protection for the composite beneath, but with sustained combat movement, crawling, rolling, and constant contact with rough surfaces, the paper layer's structural integrity would degrade over just a few days of use. These suits, honestly, were never meant to last an entire winter campaign. They were designed to provide short to medium-term thermal protection during the harshest exposure periods, while more durable solutions were being produced and distributed. Despite these limitations, the assessment from Soviet Military Medical Command was that the improvised insulation program actually contributed to reducing cold injury casualties during the critical period of late 1941 and early 1942. The real strategic value wasn't that paper replaced wool. It was, in fact, that paper prevented a total collapse of frontline fighting capacity while the evacuated textile industries gradually rebuilt their output in the East. The principles validated by the Soviet paper insulation program, well, they didn't just vanish with the end of the war. The core insight that trapped air architecture rather than material mass determines insulation performance became foundational to the development of modern lightweight synthetic insulation. Post-war materials research produced expanded polystyrene aerogel composites and hollow fiber synthetic fills, all of which, exploit the same physics that made layered paper viable back in 1941. Modern PrimaLoft and Thinsulate synthetic insulations, used in military cold-weather gear in 2026, are engineered around microscopic air-trapping fiber structures that directly descend from the wartime understanding of cellulose architecture. The difference is that synthetic polymers maintain their structure under moisture and compression in ways that wood pulp fibers simply cannot. The manufacturing logic also left a legacy. The Soviet wartime conversion of industrial paper mills to insulation production established a template for dual-use industrial pivoting under emergency conditions. Basically, the principle that existing manufacturing infrastructure can be redirected to produce military necessities faster than new production lines can be built. That principle actually appears in modern defense industrial planning documents and emergency mobilization frameworks across NATO and its partner nations. The Leningrad Siege, which lasted from September 1941 to January 1944, produced the most extensively documented cold weather survival records of the conflict. Soviet medical and supply archives from that siege confirm that improvised insulation, including paper-based composites, was distributed to civilian and military populations alike during the worst periods. The city's population survived temperatures and supply conditions that should, by conventional logistics analysis, have been unsurvivable. The paradox at the center of this story is precise. The world's most fragile industrial material was applied to one of the world's harshest survival environments and performed well enough to matter, not because paper is inherently suited to extreme cold, but because Soviet engineers understood the underlying physics well enough to compensate for paper's weaknesses through chemical treatment, structural design, and assembly discipline. Desperation did not produce this solution. Trained engineers working under desperate conditions with constrained materials produced it. That distinction, really does matter. The Red Army did not survive the winter of 1941 because of a single piece of equipment or a single command decision. It survived because at every level of the war machine, from factory managers in the Urals to medical officers in frozen field hospitals, people applied whatever knowledge they had to whatever materials were available and produced solutions that were good enough to keep fighting men alive. Paper suits are not a triumph of material science. They are, in fact, a testament to what applied knowledge looks like when the supply chain no longer exists. If this briefing changed the way you think about survival engineering and improvised military technology, subscribe to the Survival Bunker and share this video. Every share puts this research in front of someone who understands why history like this matters. Hit the notification bell. We will see you at the next briefing.